So hi everyone. I think it's time to get started with the second talk of the day. With workshops like these, which are a little bit more informal, maybe we accept that things will run possibly 5-10 minutes late, and so we're 7-8 minutes late. That's not a problem. We won't put it on you. You can take your time, and feel free to ask questions as it goes. And,
Thanks.
Yes, that was an excellent first talk, and we're looking forward to the follow-up.
Okay, thank you very much. Okay, so I already gave a bit of introduction of what I want to do in the second talk. So we already did the causal inference part. Now we're doing the orthogonal to the causal inference part, and we'll see exactly why it is orthogonal. This part of the talk will be about how can we actually model things that are really not causal in the observational setting. Which is, for example, if you look at, stock prices, or I had the motivation of gene expression that I'll go over again, but in many, many different kinds of applications, you'll see things moving together. Like, for example, when you look at stock prices, well, often, stocks will move differently from each other, but often all of them will be moving down or up together, and then some will be moving more up or more down. But very often, as here you see, right, they're all moving together in the same direction. So they show a very strong form of positive dependence, which is introduced because you have some latent variable that is introducing a strong form of positive dependence among the observed variables. And the same happens if you look at gene expression data for a particular disease. You'll see many genes moving up or down in this disease together. Or if we look at single cells in different kinds of cell types, as I said, you'll see different gene clusters moving together just because they're spatially co-localized. Right? So some transcription factor will come in and turn all genes on or off at the same time, and hence these clusters will be showing a very strong form of positive dependence. And of course, among them there will be causal structure, but not within them. Right? This is not. You cannot say that something here is causally pulling up or down something else, or here in these gene clusters there is no causal structure. There is a latent variable that is making them all move together. Okay, but in the observational setting there is no causal structure. So the question is, how can we model this? And what is the effects of it on graphical models when we actually have these these strong forms of positive dependence? Okay, so that's what I would like to talk about here. Okay, so the first question is, how do we model positive dependence? And I will just show one way of modeling it, namely the strongest form of positive dependence that is known. Okay, that's the one I'm going to use for now. Then, of course, there are questions, maybe we should be weakening it, etc. But I'll just for now be using the strongest form known of positive dependence, and that's known as this MTP2. So this stands for multivariate totally positive of order 2. Okay, a very strange name. Let's first just go through the definition. For now, it won't make any sense. I mean, to me at least, it didn't make any sense. Why would anyone come up with something this strange? So distribution is MTP2 if and only if it satisfies for any 2 points in the sample space. It has to satisfy this inequality here, where the distribution at x times the distribution at y has to be smaller or equal to the distribution of x min y and the distribution of x max y. Okay, where min and max are taken just coordinate-wise. Okay, so this is super strange. So if you think about this and the distribution is everywhere positive, then if you take logarithms, this is supermodular, right? So this is the same as log supermodularity, only if if the distribution is everywhere positive. Otherwise, I cannot do this. Okay, this is the definition of MTP2. Now, why would anyone ever want to study log supermodularity on distributions? Well, it was really introduced just as a theory concept because people were interested in positive association, right? In statistical physics and etc. And what is positive association? A positive association, so a random variable is positively associated if and only if you can take any two non-decreasing functions and the covariance will always be larger or equal to 0. Okay, so this is a form of positive dependence. And so why was MTP2 introduced? Well, MTP2 was introduced in order to study positive association because checking positive association is very difficult, right? You have to check this for any two non-decreasing function. However, and this is this famous FKG inequality, it is in fact the case that MTP2 implies positive association. And MTP2 is, well, might be easier to check because you only have to check this for any 2 points in the sample space instead of for any two non-decreasing functions. Okay, so that's really the reason why MTP2 was introduced. And nowadays, there are many different forms of positive dependence, but you can show that MTP2 implies all of them, all of the ones that are known nowadays. Okay, so this is a super strong form of positive dependence. It has not been used before for modeling, but we want to know, well, how far can we get by actually using this for modeling? Okay, and is it even useful at all? And I want to argue that it is, and it actually leads to very, very nice properties in terms of graphical models. Okay, so this is the definition. And so let's get a bit of intuition for what this actually means, right? What is MTP2, and does it make any sense to look at something like this for modeling?
So, I guess maybe you answer this question later, but computationally, if I give you distribution samples from distribution,
how do you test it?
How do you test it? And
we don't know.
Or any other positive association, computation complexity, hierarchy?
I don't know. Yes, but we don't have a hypothesis test for MTP2 yet. Yes.
You mean another hypothesis is that?
Not even in the Gaussian setting. So we know it's a mixture of chi-squares, but we don't know the mixture components. Yeah, and I have it as an open question in the end. Yes. So there is a huge amount of testing questions here. How would you do this? And actually, I'll get to that. Yeah, but all of that is open. Okay, but let me even motivate why one should care about these testing questions. Why is this actually a good thing to model with, okay? And then after that comes testing questions. Okay, so first just some properties of MTP2 distributions. So they have amazing properties, okay? So usually I call this talk, Your Dreams May Come True with MTP2, because all of our dreams come true. Anything we ever tried to prove was true for MTP2 distributions. Okay, this is really how it works. So we were at the not IMA, what is the center like next to Stanford, stats, math? AIM, yeah, we were at AIM and we started to study these distributions, and everything we tried to prove worked. Okay, so this usually doesn't happen. This tells you that the constraints are super strong, right? Because if I'm looking at the empty set, I can also prove anything I want. Okay, but this is not the empty set. So first of all, you have basically the Gaussian properties you have, like, if I have a MTP2 distribution, I take a marginal, it's again MTP2, I take a conditional, it's again MTP2. And the very nice property is that, independence is equivalent to having a zero in the covariance. Okay, that's usually only the case for Gaussians, but here actually for MTP2 distributions, that's enough, and that's just because you have this strong form of positive dependence, right? So whenever I get a zero here, I already know that I'm actually independent. Okay, so these are some very well-known properties of MTP2 distributions. And now let me tell you why, and this is something that we proved then when we looked at what are all of the properties that hold in terms of conditional independence for MTP2 distributions. This also tells you that you're completely orthogonal to the causal setting. Okay, so this is the theorem. So that's why there are many authors. This was done at AIM. So this theorem says that if you have a strictly positive distribution, which is MTP2, then this distribution is always faithful to an undirected graph. Okay, so in particular, it cannot be faithful to this graph. Okay, an MTP2 distribution cannot be faithful to this graph because there is no undirected graph that is equivalent to this one. So this is really orthogonal to causality and it matches with the intuition that we had. Okay, so this has to do with, in the causal setting, it's only causal when you take into account the latent variables, right? If you think of, there might be some physicists here, if you think of ferromagnetism and the Ising model, right? That's MTP2, in fact. So, right, it is causal if you have some latent variable that will somehow, make all of these spins go into a similar direction. But it's not causal in the observed variables. Okay, and so this is really saying that, right? But it also says something very nice. So if you take a Gaussian distribution, for example, which of course satisfies this, which is MTP2, it tells you that you can already read off all conditional independence relations just by looking at the inverse covariance matrix. Right? The inverse covariance matrix encodes the undirected graph. And these zeros will tell you everything about all other conditional independence relations. right? There cannot be anything unfaithful. There cannot just be suddenly that some effects, some walk actually cancels out with something else, and suddenly I got that x1 is independent of x2 given x3, but I cannot see it in the graph. This cannot happen. You're always faithful to the graph that you see in the inverse covariance matrix. Okay, in particular, you can never be faithful to something like this. Okay? This also tells you that everything's kind of, you have these properties that never hold, right, where you can always find counterexamples, like if I have x1 independent of x2, then if I'm increasing the conditioning set, I will always remain independent. That holds for MTP2 distributions. Something which doesn't hold in general, right? I cannot just increase the independent set, the conditioning set and remain independent. It holds here. So anything that makes sense for graphs will hold for MTP2 distribution. Okay? Because you are faithful to graph. So you can just think about it in terms of graphs, right? I'm adding in I'm removing some more variables. Well, obviously they should remain independent, and they actually do because you have this statement. Okay? So really everything you want to prove about conditional independence relations will hold. Every MTP2 distribution has a graphical representation. Isn't this the theorem? I mean, but only, yeah, if I have this property. I need it to be, yeah, so this is just because semi-graphoid is not enough, so I need a bit more. I need the intersection property. So this is the theorem, I think. But the graphical property is, it's an undirected graph, which is important. It's not a directed graph. Okay. Okay, so that's, so that kind of motivated us to look into this stuff. Like, probably this means that there will be a lot of nice properties coming up when you want to use them with undirected graphical models. But the question is the constraint useful for applications? And now I want to argue that it is. Okay? That it is super strong, but actually really relevant for applications. Okay, so first of all, just to get a bit more intuition for this MTP2 constraint. So it is a super strong form of positive dependence that will remain positive no matter what you condition on. In particular, that means that you cannot have Joule-Simpson's paradox, right? So you probably know this example. So here, if you look at, this is real data, right, which is something that is very disturbing, is because both of these are real representations of the data. If I look at here how many death sentences there were in this particular time frame, you'll see that there are more white murderers that got the death sentence than black murderers. But as soon as I, stratify this by the victim skin color as well, then you'll actually see that in both cases, there are more black murderers that got the death penalty than white murderers. In particular, there is no white murderer that got the black penalty when he killed or she killed the black victim. So that's disturbing, right? There is a switch of the correlation structure here, or of the association structure, right? Here we have more white murderers that get the death sentence, whereas here in both cases you have more black murderers that get the death sentence. So suddenly the association can switch just because I'm adding in some other variables, and I'm sure you know this in Berkeley admission rates, etc. There are so many examples of this. So Joule-Simpson's paradox cannot happen under MTP2, right? No matter what I condition on, I'll always be positively dependent. So something very, very nice, right? Again, your dreams come true with MTP2. This is a nightmare when you do data analysis, right? That things like this can happen. And it's very easy to see why. So let's just look at what it means to be MTP2 in the discrete setting. So let's just take the binary, two-dimensional binary setting. Here I just wrote down the definition again. So two-dimensional binary setting, what do I have to do? So I have to go through all possibilities of 0, 1s in the two-dimensional setting. And I have to write out these inequalities here. And you'll easily see that there is only one non-trivial inequality, namely this one here. So the probability of 0, 1 times the probability of 1, 0 has to be smaller or equal to the min of the two, so that's 0, 0, and the max of the two, which is 1, 1. Okay, so if I write this down in terms of odds ratios, this is what it means. And now you can just write down the conditional odds ratio for a three-dimensional binary distribution. Okay, so now what does it mean for a three-dimensional binary distribution to be MTP2? I go through all possibilities of 0s, 1s in the three-dimensional setting. I write down all of the non-trivial ones. You already see this is very restrictive, right? This will be exploding. But it's never 0. It always has some measure, okay? But the question, we don't know how large the measure is. That's another question. So this is it. Now you write down the conditional odds ratios, and you'll see that, whenever you have this positive, this one will be positive. Okay, so you can see that Joule-Simpson's paradox will never happen pretty easily. Okay, so this also tells you that this is a super restrictive constraint. So now, why should you still care about using it, maybe, for applications? Well, let me actually give you an example of a real data set where the sample distribution itself is MTP2. Okay, so here is a data set. This is a disease syndrome of pregnant women. Nanny Vermouth was in this group. This is a paper, this is a study that she has looked at. This is the data set that is in there. That's why we looked at it. This is the sample distribution, and you can just check that it actually satisfies all of these constraints. Okay? Now, just by chance, if I were, and here we know how large the space of MTP2 distributions is, if I were just to randomly sample binary three-dimensional distributions, only 2% of them would be MTP2. Now, we did not look through 100 distributions to find this one here. Right, so I'll have to say about, but you can already have the intuition like, well, here this is a disease syndrome, you're measuring these three variables, so probably they are positively dependent, right? So either you have the disease or you don't. If you have the disease, then the three variables will be positively dependent. That's why we looked at this particular example. This was the first one we checked, and it's actually MTP2. Okay, so yes, it is super restrictive, but there will be many examples that actually satisfy this. So it might actually be a good constraint to take into account. Okay, that's in the discrete setting. Now let's look at the Gaussian setting. So what does it mean for a Gaussian distribution to be MTP2? Yes?
So here you just verified it with the sample distribution. Is this an informal test where you want to test if the true distribution is MTP2 and you just look at the sample distribution?
Yeah, so I'm actually very surprised that even the sample distribution is MTP2, right? Even with noise and everything, it will be MTP2. So this is very restrictive. I mean, usually when you do a hypothesis test, you can even be a little bit outside, and you should still say like, I would like to have a real hypothesis test where the sample distribution wouldn't have to be MTP2, but I'm still not rejecting the model of MTP2.
Yeah,
so
can the opposite happen, that if the true distribution is not MTP2?
Yeah, but the volume is so small. So there is so much around it that I would not expect that to happen too. But the opposite should happen, right? Because I have like some point in a huge dimensional space. So I will be very often, I will be going outside.
But your 2% number here, is that the true distribution happens to be MTP2 or the sample distribution?
No, this is the true. Yeah, so here we're actually able to compute it. We cannot for 4-dimensional, we don't even know what it is. And otherwise we just sample and yeah, so we'll count how often it happens. But okay, so what does it mean in a Gaussian distribution to be MTP2? So you can always write out the supermodularity that we already talked about. And so in the Gaussian setting, it's again very easy to show that a Gaussian distribution is MTP2 if and only if the precision matrix, so the inverse covariance matrix, is an M matrix. So M standing for Minkowski here. So what does that mean? So all off-diagonal elements are smaller or equal to 0. Okay? So a Gaussian distribution is MTP2 if and only if in the inverse covariance matrix all off-diagonal elements are smaller or equal to 0. Now, when have you, for the last time, seen a positive definite matrix where all off-diagonal elements are smaller or equal to 0? Okay, super restrictive constraint. Let me talk about this maybe afterwards. But again, let me give you an example. Now, again, this is the first one I looked at. Okay, I took finance because I thought, well, they will have to be positively dependent. I just Googled small covariance matrix finance. That's all I did. And this is the first one that came up. So, already kind of nice that in the sample covariance matrix, all of the entries are positive. I took it inverse, and this matrix is exactly MTP2, okay? All of the entries, all of the off-diagonal elements are negative. Now, if I were, and here I don't know the exact number, I'm just sampling. I'm sampling correlation matrices. I'm just checking how often is a 5x5 correlation matrix has all off-diagonal elements smaller or equal to 0. Just by chance, this should never, ever happen, right? I mean, yeah, it should happen if I look at 10 to the 6 many data sets, but I didn't, right? This is the first one I looked at. Okay, so this is really crazy, right? That these data, that sample distribution itself is actually MTP2. I can find things that are close to MTP2, but that I can actually find one that is MTP2 tells you that probably this is a pretty good constraint to actually take into account in practice. Okay, and let me actually go back because I didn't say this, but I will get back to these kinds of things. So first of all, why is it smaller or equal to 0? Just to get it straight, right? So in the inverse covariance matrix, the entries are the negative of the partial correlations. Okay, just to remember. So this means that all partial correlations are larger or equal to 0, which is good, right? Because it's positive dependent. Okay. And you also already see that it's in fact a linear constraint on the inverse covariance matrix. So it's a convex constraint on the exponential family, and this will hold more generally, and I'll have the theorem there. But here you see that this will actually be a nice constraint to use, right, in the Gaussian setting. And maybe a linear algebra fact, which actually came up in the next slide. So when you have a positive definite matrix where all off-diagonal elements are smaller or equal to 0, you can easily prove that if you invert that matrix, all entries are larger or equal to 0. The opposite is not true. Okay, and that's the difference between MTP2 and positive association in the Gaussian setting. Positive association, the covariance matrix, all entries are larger or equal to 0. When I invert it, it's not necessarily the case that you're MTP2, that you're an M matrix. Okay, so this is, just having this, actually if you look at any finance data set, you'll always see that all of the correlations are larger or equal to 0. It doesn't mean directly that, it will be MTP2. Okay, this is a much stronger constraint. Okay, so this is pretty surprising, I think, and remarkable that you can actually get this. Okay, so hopefully that is some motivation that we should be looking at these, also for applications.
In simple setting in finance, you model them as single factor models.
Exactly.
What's the benefit to a single factor?
Perfect, and we can prove that any single factor model is actually MTP2, and in fact, even more, whenever you have a tree structure, it's going to be MTP2. So that's why it makes sense, right? I mean, latent tree models are used all over the case, and this is probably why these distributions actually appear in practice, because this is a pretty good model for modeling, stuff that we actually get to see. And in particular, in phylogenetics, etc., you'll actually get to see these seem to be good models, right? And they actually imply MTP2. And there are all kinds of other settings that imply. So this is why we believe that these distributions actually appear in practice, is because they're implicitly implied by many models that we use otherwise. And that's how we found these distributions. Yes. Okay, so that's hopefully some motivation. So all I want to say is, I don't want to tell you you have to use MTP2 all the time, but if you're in a setting where you would be fine with using any latent tree model, well, then you're anyways implying MTP2, so why not just use MTP2 directly and see what it actually gains, what it gets you, okay? Also, a latent tree model is a non-convex constraint, whereas this is a nice convex constraint. It's stronger, but it's maybe still good, good to do. Sorry, it's implied by it, so it's weaker, but it's maybe still good enough. Okay, so what do I want to do? So I first want to tell you what MTP2 can get you when you want to do density estimation in the parametric setting. In particular, I'm looking at exponential families in the Gaussian setting. And then I'd like to do look at what MTP2 can maybe get you when you want to do non-parametric density estimation, because it's a shape constraint after all. Okay, so maybe it could be an interesting shape constraint. Okay, so let's first look at the parametric setting. And so let's first look at exponential families. Okay, so maybe first, what is this talk not about? Okay, so this talk is not about negative dependence, and maybe you might assume that, well, I'm telling you everything about positive dependence, then you'll know everything about negative dependence. You just take, you just turn around all of these inequalities. That's not the case, okay? Negative dependence is much, much harder than what I'm telling you about in positive dependence. Unfortunately, it's not the case. So if you look at negative association, it's not the case that that's implied by the opposite inequality. Okay, so you don't have this, an MTP2, right? If I have here this in the other direction, it implies this. It's not the case the other way around. Okay, so this opposite of MTP2 is not the right notion to imply negative dependence. The right notion is this, and it has actually been done very, very recently. In 2009, it has been found what it actually is. It's this strongly Rayleigh measures. And these have also been applied in machine learning recently. Namely, when you want to do, and here there's a really nice tutorial by Stephanie Egelka and Sue Vritstra that you can actually look at. It's a NeurIPS tutorial from last year. And so these negative dependencies are very important for modeling when you want to do, for example, in recommender systems, right? If you have already bought a, hat, you're probably not so likely to buy another hat. So what you want to recommend is something that is negatively associated, right? So that you have like a big variety of things that you're actually proposing to a person to buy, and not very similar things. And so similar things have also, again, negative dependence has also been used for sparsification of neural networks, right? Because you want to be removing edges that are just measuring the same thing. So you want to have the edges be as negatively associated as possible. So whenever you want to find like somehow a big variety of things, matrix sketching, et cetera, diversity priors, that's when you want to use negative association. Okay? So that's what I'm not talking about, but there is a really, really nice tutorial. Okay, so I am talking about positive dependence, and it's much easier than negative dependence. Okay, so first parametric setting, so exponential families. So this is just the definition of an exponential family. So for example, an Ising model or a Gaussian model. So I'll call these the canonical parameters. And what is nice is that in the exponential, for any exponential family, in fact, being MTP2 is a convex constraint. Okay, so you just take your cone of canonical parameters and you intersect it with another cone, and we know exactly what the cone is. We can actually write down its dual. Okay, so for an exponential family, being MTP2 is always a convex constraint, and even nicer, whenever you have a quadratic exponential family like a Gaussian or an Ising, you can actually show that this cone here that you're intersecting your cone of canonical parameters with is polyhedral. So think of the Gaussian setting, right? In the Gaussian setting, we said that it's the non-positive orthant, right? All of the entries are smaller or equal to 0. And what are the faces in the Gaussian setting? Well, it's a 0 in the inverse covariance matrix, so that's a conditional independence relation. So this means that MTP2 is an implicit regularizer, right? When you're falling onto these faces, you're actually going to get conditional independence relations. So this should be a very nice constraint to add on because it implicitly regularizes your distribution, right? If I'm outside, which I am usually, I'm not going to be in all these nice settings. I'm going to be outside, so I'm going to be projecting onto this cone, and so I'm going to get a lot of zeros in this inverse covariance matrix. So what we're going to look at is not adding L1 penalty, right? MTP2 is just directly going to regularize the distribution. I don't need any L1 penalty, etc. So in particular, I don't need any, any lambda, any penalty parameter, because I just have an MTP2 constraint. So I don't have to worry about any of that. Okay, so this holds for any quadratic exponential family. So also in the Ising setting, I can just apply this. And you get an implicit regularizer. Okay, so what happens really in the Gaussian setting? Okay, so maybe first, these things probably people know. This is just without MTP2, right? Just to tell you all of the things that can go wrong when the standard approach for doing, for estimating a graphical model in the Gaussian setting is a graphical lasso, right? I'm adding an L1 penalty on the inverse covariance matrix. Just to tell you all of the things, if you've ever worked with these, they have such nice theoretical properties, but they work horribly in applications. In particular because, this is only going to give you the correct zero structure for a particular choice of lambda. Right? So if I'm even making lambda larger or smaller, it's not the case that I just get something sparser. This is the most annoying thing, right? If you have your lambda parameter, like how much you're penalizing sparsity, I can increase it and edges can appear that were not there before. And then they can disappear again, and then they can appear again. Okay, if you don't have any monotonicity property when you're using graphical lasso, and you only have guarantees for a particular choice of lambda, which you don't know, which you cannot estimate just from the data itself. So you need to do cross-validation, etc.
So that annoying property, is it true in general, or let's say it even is true for when the underlying distribution that you get?
It's not exactly. So I'll get to, all of this will be solved. Yes. Okay. For the graphical lasso itself, this is just in the Gaussian setting. Standard Gaussian, no MTP2. It's true. This happens.
I guess what I mean for the lasso itself, it can happen also.
Oh yeah, not graphical lasso.
Itself,
yeah.
Variables can leave the model, and then as you increase lambda, they can leave.
Yes. And it's really annoying. Yeah. And something else that I don't know why people never talk about this, but this I think is really problematic. So, if I have here the MLE, right, it doesn't depend on if I take the sample covariance matrix or the sample correlation matrix. It's invariant, right? But Graphical Lasso, it matters what you're plugging in here. Right? If you're plugging in the sample covariance matrix or the sample correlation matrix, you get out something completely different. That just doesn't make any sense whatsoever, right? That it should depend on how I'm plugging in the data. It shouldn't, right? It shouldn't depend on how I'm plugging in the data. But it depends hugely what kind of graph you're getting out, whether you're plugging in here the sample covariance matrix or the sample correlation matrix, or I'm scaling the variances in some other form.
But that's only true for a fixed lambda, but not true for the path, meaning that therefore for every lambda here there's a lambda hat. I mean there's a different lambda there.
I don't think, well, no, not if I have lambda be one-dimensional, right? I need to then have lambda be p-dimensional. Then it's true, otherwise it's not true. Yeah, you can just write it out, right? How does the diagonal, so you'll get the diagonal term here, so it matters. You need to have a higher dimensional part. So it's really annoying, I think. I mean, this is just, a statistician will probably not come up with something where it's actually not invariant. I mean, it just doesn't make sense. It's not invariant to rescaling, right? Yeah. So, but machine learning, I guess. Okay, so these are the kinds of things that are kind of annoying when you're talking about graphical graphical lasso. And so this is all solved with MTP2. So now let's look at what happens with MTP2. Oh, max entropy. Okay, so something off. So, so what am I doing here? I'm maximizing the log likelihood, right? Subject to the constraint that I'm MTP2. So this is a convex constraint, in this case, just a linear constraint. So here I have all of my entries of the inverse covariance matrix have to be smaller or equal to 0. I can write down the dual problem, which I have done here. So you have strong duality, etc. Everything in this, for this problem, you can write it out. I mean, so this is like kind of easy. And what do I want to get to? So first of all, we already saw it's a regularizer. So you'll just get sparsity for free without any penalty parameter, without any lambda that I have to wiggle around, etc. So why is graphical lasso used? Well, one reason is that you get something interpretable because you have all these zeros. The other reason is that you can actually apply it in the high dimensional setting, right? I can apply it. If I go back, I didn't talk about it. You know, in general, if I have less samples than the number of variables, the MLE doesn't exist, right? But actually here, if lambda is large enough, I can actually do estimation, even if I have more variables than the number of samples. And what is really nice, this was already proven by Slavsky and Hein in a 3-page paper or something. With 3 lines, you can prove it using ultrametrics very, very easily, is that independent of how many variables you have, if you just have 2 samples under MTP2, the MLE exists. Likelihood is not unbounded. Now the question is, how good is it? All of these proofs are not yet there, okay? But it exists, okay? So this is super strong constraint. And, you know, the nice thing is that you can actually apply it in the high dimensional setting. And independent of, you know, when you do graphical lasso, when you don't have the constraint, lambda has to be large enough if you have very few samples. Here you don't have anything like that. 2 samples is enough. And this is the other thing. So you can actually get consistent estimation without this lambda parameter. And in fact, this is not in this paper. We haven't written it out. So you can also add the L1 penalty, and you can show that it's going to be monotonic under MTP2. This is without the L1 penalty. You can get something that is consistent.
If graphical setting, but data was generated from an MTP2 distribution, then to the...
We do it as bit different than in the graphical lasso. So your lambda here is slightly, so what you're adding here is slightly different, but it's also an L1 penalty, but slightly different. But yes, then if you have an MTP2, then it's just going to be monotonic. Invariance, I would just not do this. I mean, this is just, we never do this. It's just to show that it's actually well behaved if it's MTP2. Invariance is just because we're solving that problem. We don't add this L1 penalty, so then yes, you're invariant. Exactly. Yeah, so that's why it's invariant. Okay, so this is what you get just for free when you have MTP2. Okay. So you get all these super nice properties when you're thinking about undirected graphical models just for free. So it's an implicit regularizer. You can use it in the high dimensional setting, and you get all these nice properties that you know don't need this lambda. You get invariance, or you get monotonicity if you really want to add an extra L1 penalty. Okay. Easing models, same thing. So we just did this recently. So in easing models, I mean, usually use the IPS algorithm to actually get your MLE. If it exists, we developed an IPS algorithm for the MTP2 setting, and you get the same kind of result that, in general, you need huge number of samples for the MLE to exist in an easing model. Now again, we just need, basically, like if you have a graph, you just need as many samples as the clique size, the maximal clique size, for the MLE to exist. Okay, so now suddenly you can actually apply this, right, to binary data, which is very high dimensional, where you could usually not do any of this estimation, and I'll show you an example afterwards. Okay. So it's a super strong regularizer, right? So that's why all these things become possible. But as long as you have a constraint that is actually valid for many applications, I think it's okay to make a very strong constraint. Okay, so that's in the parametric setting. Okay, and I'll show you applications come at the end. Okay, now what about the non-parametric setting? So what can we say about non-parametric density estimation under MTP2? Okay, so this is a very hot area right now, right? So there's all these papers on different, and I just have a little selection of different kinds of shape constraints for doing non-parametric density estimation. So here are some of them: monotonicity, convexity, log concavity, etc., and all kinds of other shape constraints. Under log concavity, there is a huge literature now. I just put down the first one. And I think a lot of the game is to come up with stronger and stronger constraints. So what you would like to do is somehow get to parametric rates. So you would like to have some kinds of constraints that are strong enough so that you get parametric rates, but still weak enough so that they're actually relevant for many different kinds of applications. Okay, and that hasn't been achieved yet. Okay, so there are constraints where you get something that is parametric, in particular log concavity plus all kinds of additional assumptions on it, but probably not as relevant yet. So one of our hopes, and we don't have any proof or any counterexample yet, is that something like MTP2 plus something will actually give you that, right? Because we know it is super restrictive. We also know it is actually relevant for many applications. So maybe it could give you something like parametric rates. That would be the hope, and that was kind of why we even started looking at this. Okay, so let's look at this problem. So what I want to do is the non-parametric setting. So I want to maximize directly over density functions. I'm looking at maximum likelihood estimator. So here I'm summing up over all my samples. So this is an infinite dimensional optimization problem over all density functions. And my shape constraint is just going to be MTP2. Okay, so what is the problem in general is, why do you even need shape constraints? Well, if I have my samples, if I don't have any constraints, right, then I will just put infinite mass here. So I have these spikes. So that's not very interesting, right? That I just say like, oh, I'm super confident that my density just has mass on my samples. And unfortunately, even under MTP2, that's still the case, right? So if my samples are like this, then actually it is MTP2 to just put infinite mass here, 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 and here. So I need something stronger than this. Okay. Because what is MTP2, right? It's just that this times this has to be smaller or equal to this times this. So if I put infinite mass there and these are on a square, if they're not on a square, I just add one more sample and I'll just put infinite mass everywhere. So this is not strong enough to get anything interesting. So now you can do anything, and this is like really just a choice that we took. We just, as a first thing, looked at adding log concavity. You could add anything else. So why did we add log concavity? Well, this is log supermodularity. This is log concavity. So hopefully the two things are interacting nicely. Right, one is, they're both things on the second derivative. One is entry-wise and one is positive definiteness constraints. So hopefully they would interact nicely. Also for log concavity, this has been studied a lot, and it's a kind of natural assumption because it gives you, continuity, and it incorporates many, many different kinds of distributions. But this is an arbitrary choice that we made. Now, why log concavity gives you something really nice? Well, in log concavity, Kuehl, Samworth, and Stewart, so what did they show? Well, so this maximum likelihood estimation in the non-parametric setting is a infinite dimensional optimization problem, right? I'm optimizing over all these density functions. Now, what did they show? Well, they showed that, first of all, that if you have just as many samples, or 1 plus the number of variables, the MLE actually exists. And they showed that it is actually can be computed as a finite dimensional optimization problem. Because they showed that the MLE is always a 10th function, where so these are my samples. This is an R2. This is the density. So here are my samples. They showed that it's always a 10th function with 10th poles at the samples. So that means, right, instead of optimizing over all density functions, if I'm just optimizing over 10th functions with 10th poles at the samples, I have a finite dimensional optimization problem where the dimension is given by the number of samples. Because I'm just optimizing over these 10th pole heights. Okay? And it's a convex optimization problem. So this is super nice, right? So this infinite dimensional optimization problem becomes a convex optimization problem. When you have when you want to do log-concave density estimation. So now the question is, under MTP2, is that still the case? So first of all, and I think this is still a nice result, and then comes something that we're not completely happy with, but so first of all, we ask, well, how many samples do we need for the existence of the MLE? So before, and now this is kind of nice, so before it was, for just log concavity, you need dimension plus 1 many. In the Gaussian setting, we said 2, right? So Gaussian MTP2 is log concave. So if we just do MTP2 and log concave, we just need 3. Okay, so this again says that, well, this is not so much worse than Gaussian. I mean, at least from here. The intuition is that it's not that much worse than Gaussian, right? We went just from 2 to 3. Again, it doesn't depend on the ambient dimension of the problem. So just with 3 samples, the MLE actually exists. Now the question is it always a 10th function? Now the problem is, so the other proof is actually very easy to show that it's a 10th function. Here, this proof here doesn't give you any insights in terms of what is the shape of the MLE, okay? It's just, it just uses convergence properties of log concave distributions, etc. So the question is it a 10th function? So can we solve it as a finite dimensional optimization problem or not? Okay, so we can, if we are in we can prove it if we are in R2 or in the binary setting. Then it is always the exponential of a 10th function. This is how I write 10th functions. So these are the heights and these are the poles. And again, this optimization problem is actually convex. So this MTP2 constraint is a convex constraint on the 10th poles. Now, why can we, so the conjecture is that this is true in general. Okay, that's always a 10th function. Why can we not prove it? So there is a problem, namely for supermodularity. So if you just think about a supermodular 10th function, in R2, if I know, so I take a 10th function, if I know that the 10th poles, that at the 10th poles I'm supermodular, it means that the whole 10th function is supermodular. Unfortunately, this is not the case in higher dimensions. Okay, even though it's a 10th function and I know that at the poles I am supermodular, it's not in general the case that the full function is supermodular. So what our conjecture is not, so you definitely have to add in more poles than where you have your samples, because this we can actually show which ones we have to add in. And we conjecture that in those added in poles, this will actually hold. And in all of the experiments we've done, this holds. Okay, so it has to be very special 10 poles and then this holds, but we just don't have a proof. So we have an algorithm in the paper which either outputs something that is MTP2 and then MLE, and you can easily check that it's MTP2, or it doesn't, and then you have a counterexample to this conjecture. Okay, but then we also have a stronger constraint at MTP2 where we can actually prove that it will output that. So if this doesn't hold, then at least we have something stronger than MTP2. Okay, so this is as much as we know for non-parametric density estimation. So I think there are still a lot of open questions. In particular, I think we really want to know, like these, do you get parametric rates with something like this, right? Is this actually strong enough to get something really nice? I mean, there are hints that this is the case, but that it doesn't depend on the ambient dimension, etc., but it's not clear yet. In particular, as long as we don't have this proof, it's like very hard to do anything more. Okay, so just to show you how it works, if you just have, in this case, I think we had 50 samples in R2. This is from a Gaussian. So this is an example of a MTP2 log concave distribution, right? And the standard Gaussian is MTP2 and log concave. This is what you get when you do log concave density estimation. This is what you get when you do log concave and MTP2. Right? This looks so nice like a Gaussian, just because it's a super strong constraint. So it should get you quite a bit more. There are all kinds of questions in terms of how to do this, efficiently in the high-dimensional setting, etc. We don't have any of that, but at least you can solve it with conditional gradient descent, at least right now. Okay, so there is some hope. So now let me just tell you about applications in the parametric setting. So this is the application that I think we were very happy about in this easing model paper because, so this is the kind of study that, in general, you can't just run easing models, right? So here I have like 9,000, so I have 16 variables, binary, and I have 9,000 individuals. But, most of these individuals don't have the symptoms, right? So 5,600 of them are in one of the entries. So this is a contingency table of size 2 to the 16. One of the cells has huge number of samples. Most of the cells don't have any samples. So the MLE in the easing model doesn't exist, right? So there's nothing you can do in that setting. But actually, under MTP2, you can run this. You can actually do estimation under MTP2 for this particular example. This is how the correlation matrix looks like. So this is some depression and anxiety disorder data set, where there are some variables which are known as bridge variables, like, that you cannot sleep well is in this disease, but it is also in this disease. And similarly, there are some others. This is concentration problems, which is here and here. And there's one more, fatigue, which is here and here. Okay, so there are 3 bridge variables. This is how the graphical model looks like, so the inverse. So this J matrix in the easing setting. And, this, in this psychology paper, there are psychologists who just give an interpretation of what they think about these variables, and they exactly describe it like this, that here, this they call the causal skeleton, this star structure here. They believe, just from intuition, that this depression variable is actually the cause of seeing all of these other correlations that you see here. This is what they call the causal skeleton. They didn't get this graph. I mean, this is what they drew by hand, but this is exactly what you get under MTP2. You actually get to see this causal structure, and you get to see that, the strongest links between the 2 diseases are exactly between these bridge variables. So you just get out everything just directly, right? What was done before in terms of intuition by different kinds of psychologists. So I think you get very nicely highly interpretable results just directly out just by applying MTP to this data set, which now you can do before you couldn't if you just have easing model. And finance, I suddenly started to like finance. Why did I like it? Because it's easy to show that you do well, because it just depends on how much money you make, which is not like in genomics where you have to argue that you're actually doing something reasonable, right? So here they have like some, and I never did finance before, so here we have like some information ratio, which is just a ratio of average returns to a standard deviation of returns. We take this like large data set with all of the different stocks in there, and MTP2, we didn't develop it to do finance, right? So in the paper, we actually have many, many more different kinds of models that people have used. There are models that people have been introducing just for finance. In particular, we also now have the nonlinear shrinkage, etc. Like really methods that were just introduced for finance, but just plain MTP2 does better than all of them. Just like this, right? It wasn't introduced for finance. I mean, I'm sure you can do better than by adding some kinds of constraints onto your MTP2 estimator. But it just suggests that, this structure just makes sense for finance data sets, that you add this MTP2 constraint. Because you do have these latent variables that are affecting many of the stocks together.
Say again how you evaluate the quality of the model?
Yes, but we just use what they care about. So we have actually 2 plots in here. So one is this information ratio. So I'm going over time, okay? And at the beginning, I'm investing based on so I estimate the covariance matrix. I plug that in. I estimate the weights based on this Markowitz portfolio, and I'm investing based on the weights that I get out. Then I see how much returns I get. I do the same thing for the next. And over this whole time period, this is how much you would get out. Which one? Sorry. The minimum variance or something? So
no, like the optimal static mixture of investments. So every day you invest according to the same split of your capital, and then you optimize this split.
Optimizing based on like looking forward or what?
You can learn it online. You can make.
So I don't know. So probably we haven't done this comparison, and we should probably do it. We just took whatever We worked together with some people in finance and, told us which ones they would care about, and we just compared to those.
The difference is potentially some level of philosophical, right? Because here, one is actually doing progressive model assumption, and then, if I understood correctly, from universal setting, you're really trying to a bigger driven. So you're not really estimating the model the way she's trying to.
Oh, I see. So you don't even look at this problem, right? So you don't even optimize this, I guess.
Use something else.
Okay, no, so we only looked at this particular model, and where we're plugging in a covariance estimator, and then we're using the weights that come out of the Markowitz problem, the optimized weights for that. And then,
but I guess that's the portfolio you want under the assumption that this model is correct.
Correct, yes. So I'm here estimating, I'm looking at different covariance matrix estimators, is what I'm comparing really in this plot. And I'm saying that this covariance matrix estimator is useful for finance. And they need to solve like very, very large covariance matrix estimators.
Fundamentally, all the algorithms, they use the same data, they use the same probabilistic models.
Correct.
But estimation algorithms for covariance matrix
is different.
And hence.
Exactly. So this is all I'm comparing here, is like how good of a covariance matrix estimator is my MCB2 estimate.
And it's also one of the reasons why many of the parameters on Causal models actually use these kind of data sets to evaluate.
Yes. Yeah. Yeah. But I think it's still surprising because we never, did this for finance, right? So.
And the number that we expect here, higher the number, better.
Higher the number, better, because it's average return to standard deviation of return. Yes, and then we also have the one where you look at the minimum variance Markowitz portfolio, where you just look at the standard deviation, and the plot is actually very similar. Just didn't put it here because I think this is the more relevant one. Okay, so with that, let me end. I hope I was able to convince you that total positivity constraints are anyways implicit in many different models. They reflect real processes and are maybe useful for different kinds of applications, in particular when you want to use models that